I guess hopefully more students are still watching the videos and whatnot and haven't given up at this point. But um, we had the lecture quiz on Monday. So we had the second lecture quiz on Monday. The second lecture quiz covered one-way ANOVA and a little bit about multiple comparisons, a little bit about contrast, and then a little bit on some of the CRBD stuff too. So I haven't had a chance to look at the quizzes yet. This is certainly something I'm going to get to soon. It's just I had every single lecture that I taught had a midterm or a quiz within 2 days of each other. So it's kind of just I'm almost on the 151 stuff, and then I'm going to start the 350 stuff, and then I'm going to do the 252 stuff. But I'll have I should have the results of the quiz back to you before Monday. So I try and get it all marked within a week of the writing date. I had a couple of, kind of like comments or, some concerns, I guess would be the right way to express that after the quiz. So I think in particular, I guess some students felt like maybe the quiz was a bit too long for the hour period. A couple of students felt that the question 5 with the ANOVA tables was confusing and whatnot. So my my goal, in response to those comments, the first thing that I really need to do is see how the majority of the students did, right? So we're a class of about 30 students. So I got feedback from 2 students. So that's, 1/15 of the class effectively. So that doesn't make the comments any less valid or anything like that. It's just that I want to see how the results played out across the whole class before I start jumping to any conclusions, which I hope you can understand. But once I see the results and I see how things are turning out, if it's in fact the case that a lot of students weren't able to complete the test and that a lot of students really struggled with particular aspects of question 5, which had the 2 ANOVA tables, then I'll make adjustments as I need to and whatnot. And I'll certainly put some time aside to go over that with everyone if that is in fact the case. But just outside of that, I just want it to be clear that even though we're in an online environment and whatnot, it doesn't mean that I take any of this stuff any less seriously. Like I still want everyone to do well, and I still want the quizzes to be considered fair and all these sort of things. So like I said, once I have a chance to go through them, look at the grades, see how the class did as a whole, it'll help me just build a better picture of what I need to address moving forward. And as I said, I'm going to try and get all that stuff. Right. Yeah. So, right. So, sorry. And then, as I said, I'm just going to try and get I'll try and get all the grading done within a week so that by Monday next week, we can have a more thorough discussion about the quiz and whatnot and that sort of thing and go over some of the concepts. Yeah, I mean, like in response to that comment, I mean, I'm not really sure what to say. Like these things happen on quizzes. I mean, testing is a tough environment in general. I don't necessarily think it's fair to say it's the best way to assess student knowledge, but I mean, that's a completely different discussion, I think. And, I mean, certainly going forward, we can look at little extensions in time, five extra minutes or this kind of idea, just to try and alleviate some of the stress of getting the photos done and whatnot. Yeah, no, I appreciate it. I wish I could give you better feedback on that. That's all. Yeah. Well, I mean, certainly this would be something to consider going forward. With respect to like from my end, like I said, once I see the bigger picture and I have a better idea of how the class did as a whole, I can adjust the number of questions for sure and try and make it a little bit shorter to try and give that extra time in the hour slot. I mean, I didn't feel that the test was unfair in terms of length, but I can understand how getting stuck on like one spot of it would make it difficult to get through the rest of it, right? I mean, it only takes one question to rattle a student sometimes, then like the whole thing gets thrown off. So, you know, from my point of view, I'll try and do a better job of like making sure the quizzes fit into that hour time period, and you know, maybe giving a little bit more clarity. I mean, one student sent an email and gave a good suggestion for clarifying a question. I mean, certainly this is something that I will try and do a better job of going forward. Every semester we tend to get feedback on that kind of thing, like just trying to make it really straightforward. I hope that like from my side of the desk, like even though it is a quiz environment, I'm still trying to encourage like thought and kind of create creative answers. So for example, like the one question where there is the three population means and it said define a contrast in the context of these three population means. Like it's a fairly open-ended question because there's many different ways to do that, but all you really need to touch on there is, you know, well, you have to have coefficients in front of the means that add to zero, and they all have to be linear. But you can use any example you want to contrast those three means. But the comment was that you should, you know, just make it clear that you can state any example you want. So from my point of view, there are questions like that, like the definition questions. Sometimes they're supposed to be a little more open-ended to encourage thought and to see what kind of creative answers we can get back in the context of that problem. Like what I don't want to do is always make it really instruction based where it's like do this and then do this and then do this and then do this, because I feel like that takes the thought part out of it completely. And there still has to be some, you know, challenge associated with it. Like if it gets too instructional and direction based, I just feel like you're losing out on that aspect of the material. Um, but yeah, as I said, I mean, all of this could be a moot point, you know, if everyone ends up just doing really well, I suppose. But once I get a chance to look at it completely, you know, adjustments that need to be made will be made. I mean, I'm not trying to get anyone or anything like that. It's just, I don't know. Sometimes quizzes are sometimes, I guess sometimes they're trickier than you think they're going to be when you set out to write it. But yeah, like I said, well, I'll take, once I get a chance to like sit down and go through them and see the marks and the distribution of the marks and all that kind of stuff, I'll have a better idea of how everyone did as a whole, and then I'll be able to address, or at least hopefully give better feedback on some of these concerns. Okay, does anyone else have any comments or questions in relation to that just before I move into the lecture material? Yeah, okay. I mean, just in regard to the time thing. So the typical rule of thumb that we use for writing a quiz or a test is that the student should have roughly 3 to 4 times more than what it would take me to finish the test. So that kind of exam, like I'm writing that in within like 15 to 20 minutes, let's say, if I like sit down with just the tables and whatnot. Again, the comparison is a little tough because like I know the questions and whatnot, but that's like the general rule. Part of test writing is time limit. So while I can appreciate like 5, maybe 10 extra minutes, like I don't think that's a big deal. Um, you have, like, you just have to take into account that that is part of the assessment, is the fact that there is a time on completion. So again, I'm going to try my best to get everything to fit within that hour, well, 70 minutes. From start to photos to like all that kind of stuff. But again, like part of it is that there is a time limit. So I just hope that you can appreciate that is all. Yeah, I mean, there certainly like there will be ways to look at adjusting it, whether it's like one less part off like a question like number 5, or like one less definition question or something like this. I mean, one way or another, I'll try, like I will aim to find like the right balance for the quizzes. Like what I was looking at was effectively trying to keep them the same weight, right? So it's like 3 quizzes, each quiz is around 10%. I didn't want one quiz to be, 30 marks, and then the second quiz to be like 20 marks kind of idea. And when I weighted it out and I looked at the type of problems, it was like that was a 30 mark quiz. So that was part of what went into it for me, from my side of it. But like I said, I'll do my best to for the third one in particular, to try and make sure that it's really structured to fit within that 70 minutes with the time for submission and whatnot. But okay, so any other comments or questions? Okay. Okay, so I'm not seeing any, so I'll move back into the material now just so we can keep pushing through. So we are currently working through lecture set 8. And lecture set 8 is devoted to the sign test. The sign test is a non-parametric hypothesis test. What we mean by non-parametric hypothesis test is essentially the sign test does not assume a distribution for does not assume a distribution for the population that we are studying. So in the sign test, we effectively no longer have to consider that normality assumption, which is the main motivation for this particular suite of tools. Now, the sign test, just like any other hypothesis test, is carried out in a 6-step process. So on the first step, we have the null and the alternative. On the second step, we have the significance level. On the third step, we have computation of the test statistic. On the fourth step, we have p-value computation. Notice that with the sign test, we are strictly using a p-value. There's no critical value in this particular situation. And then on the fifth and the sixth step, we have decision, which would be based off the p-value, and interpretation of the results. All right. So we left off last class talking about the p-value. So the p-value is going to be based off of the test statistic the same way that it was for any of the other hypothesis tests that we have talked about. The p-value is effectively the test statistic is a count of the number of values above or below the hypothesized median. In the case of the two-tailed test, it's actually the maximum of both of those. When we are using a sign test, we are actually assuming that the test statistic is binomially distributed with a probability of success of 0.5. Okay, so that means that our test statistic is going to be computed using the binomial probability formula. And this is something that we had touched on last class, but just as a reminder, the binomial probability formula is shown in equation 1, and it's read as n choose x. So that's the first part here. This thing is choose. X is going to be the test statistic in this case, the value of the test statistic. And little n is going to be the number of observations in the sample that are counted towards the test statistic. All right. Okay, so we're going to look at a couple of examples of how to conduct a sign test. This first example is going to utilize what we have described so far. So basically what we're doing here is we're setting up a hypothesis test about the median of the population. And then on the fourth step, we're going to use the binomial probability formula to compute the p-value. We're then going to look at another example of a sign test, but in the second example, we're going to talk about a normal approximation for p-value and critical value construction. And the benefit of this normal approximation is that it brings computation and of the p-value and the critical value back into the area that we understand, or an area that we have a lot of familiarity with because we'd be using the standard normal table. Okay, so a sign test would look something like what follows. Okay, so first off, we have sort of a standard description of a problem. So we have the following measurements or breaking strength of a certain kind of 2-inch cotton ribbon in pounds. Okay, so each of the values in this table are breaking strengths in pounds. So these are all LBS and they are associated with the breaking strength. At the 5% significance level, do the data provide sufficient evidence to conclude that the population median exceeds 160 pounds? Okay, so let's start off by noting a couple of things, okay? So the only real assumption that we have to validate here would be the simple random sample assumption, because we're going to be using this sign test, but just for illustration, okay, let's just assume it's not clearly stated, but we'll just assume this is true for now. And then the normality, let's say, cannot be validated. Okay, so what we're doing here is we're setting up this idea of requiring an alternative kind of test. So up till this point, our approach has been conduct the test anyways, and then make a note that we need to validate the assumptions in the conclusion. Now what we're going to do is we're going to say, okay, we can't assume normality. It isn't reasonable. So we're going to take this non-parametric approach. Okay, so we'll take a non-parametric approach. Okay, so in particular, we're going to use the sign test. So our sign test, again, is a non-parametric alternative to our one sample t-test or our one sample hypothesis test about the single population mean. All right, so on step one, we're going to express our null and alternative hypothesis, but in the context of the population median. So one of the main differences between this style of testing and the original style of testing that we considered was the fact that we are now using the median rather than the mean. So we have H0 eta equals 160, or sorry, eta less than or equal to 160. Versus HA, eta is greater than 160. Okay, so the setup is pretty much the same as it was before. The only difference here is that we have eta, which represents population median, rather than mu, which represents population mean. All right. Okay, so maybe I'll just move everything over. Okay, I'll just leave it like this. Sorry, here, I'll do this. This will make more sense. Okay. All right, so now what we're going to do is we are going to count the number of values that are above the median. So we are conducting an upper tail test. So S, which is our test statistic, is going to be equal to number of observations above 160. All right, so if we work through the table, we can just start by labeling the values that are above 160. Okay, so I'll use a plus to mean above, and I'll use a negative to mean below. Now, one of the things that we have to watch out for are situations where one of the observation matches the median. So for example, here we have a 160. So we're going to scratch that one out. So this value is no longer going to be considered in the remainder of the test. So we knock this 160 out because it's equal to the median. Then we have another plus, another plus, another plus, another plus, minus, plus, plus, minus, plus, minus, plus, 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 plus. Okay, so in total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so our test statistic here for the sign test is equal to 15. So it's simply a count of the number of values that are above the hypothesized median. Any questions so far? Okay, so it's an upper tail test. So our p-value is going to be the probability that s exceeds little s. So basically the probability of observing a value greater than the test statistic. We are using a binomial probability calculation here. So this thing can be written as the probability that s is greater than 15, which is equal to the probability that s is greater than or equal to 16. Okay, so now what we have to do is compute this probability using the binomial probability formula. We removed one observation from the data set because it was equal to the median. So this thing becomes the probability s equals 16 plus the probability s is equal to 17 plus the probability s is equal to 18 plus the probability s is equal to 19. So notice that we are stopping at 19 because we only are considering 19 values from the data set. So now what we have to do is plug into the binomial probability formula. So here we're going to have 19 choose 16, 0.5 to the 16, 1 minus 0.5 to the 3, or sorry, let me write that out. 19 minus 16 plus 19 choose 17, 0.5 to the 17, 1 minus 0.5 to the 19 minus 17, plus 19 choose 18, 0.5 to the 18, 1 minus 0.5 to the 19 minus 18, 19 choose 19, 0.5 to the 19, 1 minus 0.5 to the 19 minus 19. Okay, so you can see that this approach is quite cumbersome, especially if you have a test statistic that's not that close to the upper boundary. Like there's many of these different computations you could potentially have to make. So another reason why this normal approximation we're going to see on the next slide, it can be very beneficial to us because it can really help us reduce the amount of work that goes into this p-value computation. Okay, so now we have to work out each of these values. So this can be done by hand, just by working out the combination rule there. And we should end up with something like what follows. plus 0.1234519. Okay, and then that gives us 0.0022125. All right, so now we're back into our usual sort of role. So on step 5, we can say reject H0 since the p-value, which is 0.002, is less than alpha, which is 0.05. And then on step 6, we can say at the 5% significance level, the data provide sufficient evidence to suggest that the population median breaking strength exceeds 160 pounds. So for the most part, I hope you might agree that the test is pretty much unravels the same way as any other hypothesis test. If on step 3, the computation of the test statistic is pretty straightforward. We're just counting the number of values above a particular point. Step 4 is a bit of a pain. You know, there's not much of a way around it. You know, we have to work out all these different binomial probability formulas. But after that, everything is pretty much the same as it was before. So we have a direct comparison of the p-value to the significance level. In this case, we're going to reject because the p-value is less than alpha. And then on step 6, pretty standard conclusion. The only difference is that we're talking about the population median now, not the population mean. Anyone have any questions? Breaking, median breaking strength. Okay, so as I had mentioned when we were working through the p-value for the first illustration, it's kind of a pain having to use the binomial probability formula in each of those different situations. Fortunately, for the sign test, we can actually use a normal approximation for the test statistic when we have a sample size greater than or equal to 10. So we don't require much information in order for this normal approximation to come into play, which again is kind of nice because we're sort of getting past the normality assumption on the data. And then we're basically saying, well, as long as we collect more than 10 observations, we can approximate a normal test statistic using the count of the number of values above or below the median point. So basically the way that this is going to work is when we have a sample size greater than or equal to 10, and we want to use the sign test. On step 3, we'll compute S the same way that we did before, which again depends on the direction of the test, but the idea is the same. So we'll then compute S, and then we will transform S into a Z-score using equation 2. And then once we have the Z-score, we can then conduct step 4 of the test using either the critical value or the p-value approach, the same way that we did way back when we first reviewed hypothesis testing in lecture set 2. So we're kind of finding a workaround here to bring ourselves back into the realm of normality. So you can kind of see normality is kind of like a gravitational pull for us, and we want to continually kind of push our way back to it because it's so familiar and easy to work with. Okay, so to demonstrate this continuity correction, we're going to look at another sign test example. This is basically the same idea that we just had, except because we have 40 observations in this data set, we're going to be able to apply this approximation. And actually, we would have been able to do it for the first example as well, because we had 20 observations. So we could go back, compute the normal value for the first example, and then compare it to the result we had using the binomial probability formula to see if there's agreement. So that might be kind of an interesting exercise for you if you're going to review the material. Okay, so in this particular example, we have measurements of the amount of sulfur oxide emitted by a large industrial plant over 40 days. So we have 40 observations. At the 1% significance level, do the data provide sufficient evidence to conclude that the population median is different from 21.5? All right, so same starting point as before. So we'll just make a quick note here. All right, so probably going to be sort of hard to say that this is true. It's not really a simple random sample because it's just data collected over consecutive days, which is more kind of a systematic sample, if anything. So let's say that this isn't true based off the description. So we'll have to make a note of that going forward. All right, and then for normality, we'll also say that this can't be verified based off of the description. Okay, so we're gonna use a sign test with acknowledgements that we need a SRS. Okay, so step one, pretty standard here. So we'll have H0 eta equals 21.5 versus HA eta different from 21.5. And then on step two, we have alpha equals 0.01. Okay, so on step three, we need to count the number of values below 21.5, the number of values above 21.5, and then we're going to take the maximum of those two. So same declarations as before, we'll use negatives and positives to count, to mark which ones are below and which ones are above. So negative, positive, negative, 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 positive, negative, 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 positive, positive, positive. Let me just make sure. I just want to check something really quick here before I, yeah, maximum of those two. Okay. Negative, 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 positive, negative, positive, negative, negative, positive, negative, positive, negative, positive, 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 negative, negative, positive, positive, negative, positive, negative, positive, negative, negative. Okay, so S negative, S positive. Okay, so positives, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Did I get that correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, which means that we have 23 here. . Okay, so our test statistic is the maximum of S negative and S positive. Okay, so that's going to be 23. Okay, now what we will do is we will say, since n is greater than 10, z is equal to s minus 0.5 minus 0.5 times n divided by 0.5 times the square root of n. So we will have z is equal to 23 minus 0.5 minus 0.5 times 40 divided by 0.5 times the square root of 40. My guess will be so we have 22.5 minus 20 divided by 0.5 times square root 40. 0.7906. Actually, it's a z score, so I don't really need to keep that many decimal places, but whatever. Right? Okay, so now on the fourth step, we can do our standard critical value approach or our p-value approach using the standard normal curve. So if we take the critical value, zero. Okay, so here's z 0.05. Right, so this is our rejection region. Does anyone remember what the z score? Oh, it's a two-tailed test. Sorry. This will be z 0.025, and this will be negative z 0.025. All right. Does anyone remember off the top of their head what the z score is? So this would be the same as the z score for a 95% confidence interval. Yeah, very good. So that's 1.96, negative 1.96. Okay, and then we can verify, or we can show that the test statistic is clearly not inside the rejection region here. Right, so we're not going to reject based off the critical value approach. And then if we take our p-value approach, oh crap, yeah, you're right. It does make a difference though. I mean, not in terms of result, but we should be, we're not, that wouldn't make sense. That would be very confusing. Okay, so good catch. Thank you, Megan. Okay, well, that was still the correct answer for the 95% interval. Does anyone remember what the z-score for the 99% interval is? I think it's 2 points. Oh, that one I can never remember. Where are my tables? Okay, part 2. Okay. 2.576. So this would be negative 2.5. All right. Okay, so then our p-value is going to be 2 times the probability that z is less than negative 0.79. So this will be, and if we go to our standard normal table now, and we look up negative 0.79, here's negative 0.7, 0.09 is in the last column here. So that gives us 2.148 in the lower tail. And that's going to give us a p-value of 0.4296. All right. So then on step 5, we can see that we do not reject H0. And then on step 6, we can say at the 1% significance level, the data do not provide sufficient. Actually, sorry, we need to note that one other part there too, don't we? I think. If the SRS assumption can be validated, the data do not provide sufficient evidence to suggest that the population median amount of sulfur oxide differs from 21.5. Oh. No, did I seriously? All right, well. Oh, no, okay, cool. That would have been embarrassing. Good stuff, good stuff. All right, sweet. Any questions? So those are two sign test examples, one using normal approximation and one traditional sign test. Again, if we have 10 or more observations, we can use the normal approximation. Yeah, so the original formulation, so basically in the situation where you can't use the normal approximation, so say that you have a data set with 9 or less observations in it, there's only a p-value approach. But if you can use the normal approximation, so if you have a data set that has 10 or more observations in it, then you can write the test statistic as a z-score, and then you can do either the critical value or the p-value. Okay. So again, this is an example of an alternative to a one sample t-test or a one sample z-test. So the sign test is the non-parametric version of our one sample t-test or our one sample z-test. We can use the sign test to conduct the 3 standard hypothesis tests. The big difference though is just that the hypothesis test is formulated about the median. It's not formulated about the mean. And again, if we have 10 or more observations, we can use a normal approximation, which just means that step 3 or step 4 unfolds like it would have for a test based off the standard normal distribution. So then we can take the critical value or the p-value approach. Okay, so in lecture set 9, we're going to talk about what is called a signed rank test. And just to give you a little bit of a idea of what's going to happen here. So the signed rank test is also an alternative to the one sample t-test. And actually the signed rank test is the preferred approach when you want to do a non-parametric one sample test. So the signed rank test operates in a very similar way to the sign test, except that it also takes into account the ranks of the values. And in that sense, it doesn't waste information in the same way that the sign test does. So in that, like what I mean by that is the sign test is just a count of the number of values above or below a specific point. The signed rank test also does the same thing. So it counts the values above or below, but then it also ranks them in terms of how far away they are from the hypothesized value. So we're going to see the signed rank test in two different ways. We're going to see it as a one sample test, and then we are going to talk about it as an alternative to the paired t-test. So you might recall that a paired t-test is effectively just a one sample test. So the paired t-test takes the differences between every pair of values for each observation, and it creates one sample of differences. And then basically we just do a one sample t-test on the differences. So the sign test or the signed rank test, which will be our preferred approach here, we can use that as an alternative to the one sample procedure, and we can also use it as an alternative to a paired t-test. So on Friday, I'm going to walk you through the steps of the signed rank test. One of the things that we will do here that we haven't done before is talk about the derivation of the sampling distribution. So this is, to me, is probably one of the most interesting parts of the course, because you can see how like we're just going to use logic to understand how the test statistic behaves. And then from that, we'll be able to find p-values and critical values. So the bulk of the material is not different from what we saw before. 6 steps, same goal. We can use it in a one sample case or a paired sample case, but we're going to add a little bit extra here and talk about the sampling distribution of the test statistic in some detail. And then we'll work through our examples. We're also going to introduce a new table. So I'll get that posted for everyone, and we'll talk about how the table works on Friday as well. But outside of that, we're just going to continue through the non-parametric stuff. And again, our sign test is the non-parametric one sample t-test. The signed rank test, which is lecture set 9, is also a non-parametric one sample t-test and a non-parametric paired t-test. All right. So if you guys have any questions, please let me know. Again, I'll try and get all the midterm stuff wrapped up by Monday so we can have a little bit more detailed discussion on it. Quiz stuff wrapped up by Monday. And otherwise, have a good couple days, and I'll talk to you on Friday.